Welcome to our introduction to materials and textures. At their core, these two concepts are the building blocks that bring the digital world to life. Imagine a technically perfect 3D model of a car or a building. Without materials and textures, it's just a lifeless, colorless shape. It's the application of a glossy red paint, the rough texture of asphalt beneath the tires, and the reflective properties of glass that transform that simple model into a realistic and communicative design. This process is absolutely fundamental across a vast array of industries. In architecture and engineering, it allows clients and stakeholders to visualize a project long before a single brick is laid. In product design, it's crucial for creating compelling marketing imagery and prototyping different finishes. And in the worlds of film and animation, it's the very magic that creates believable characters, fantastical creatures, and breathtaking environments. Throughout this presentation, we will explore how these elements work, from the basic properties of light interaction to the advanced workflows that professionals use to create the stunning visuals that we see every day. Our goal is to understand how we move from a simple geometric form to a rich, believable, and emotionally resonant final image. So how do we actually see these materials and textures? The answer lies in a process called rendering. Think of rendering as a virtual photo shoot. It's the process where the computer takes all the data in our 3D scene, the models, the lights, and most importantly the materials, and generates a final 2D image. At its heart, rendering is a sophisticated simulation. It calculates how virtual rays of light would travel from a light source, bounce off various surfaces in the scene, and finally enter our virtual camera. The material assigned to an object is the rulebook that tells the light what to do when it hits that surface. Should it be absorbed? Should it reflect like a mirror? Should it scatter softly like it would on a piece of paper? Or should it pass through, bending as it goes, like with glass? The rendering engine simulates all these complex interactions for every pixel in the final image. This process can be incredibly computationally expensive, sometimes taking hours or even days for a single frame in a high-end animated film. But it's this meticulous simulation of physics that allows us to create images that are often indistinguishable from reality. Rendering is the crucial step that turns an abstract collection of data into a tangible, visible piece of art or design. So to create any material, we first need to understand its fundamental properties, the basic levers we can pull to define how it looks. Let's start with the most intuitive one: diffuse color. This is the base color of an object when it's hit by a uniform white light. The red of an apple, the blue of a plastic cup. It's what we think of as the object's intrinsic color. Next, we have specularity. This property controls how shiny a surface is. A material with high specularity, like chrome or a mirror, will have very sharp, bright highlights. A material with low specularity, like chalk or dry terracotta, will have very soft, muted highlights or none at all. Then we have properties that deal with light passing through an object. Transparency, or its inverse, opacity, determines how see-through a material is. A pane of glass is highly transparent, while a concrete wall is fully opaque. Closely linked to this is refraction. When light passes from one medium to another, like from air to water, it bends. Refraction is the measure of how much it bends. This is what causes the classic bent straw illusion in a glass of water, and creates the beautiful caustic patterns at the bottom of a swimming pool. Mastering these four core properties of diffuse, specularity, transparency, and refraction provides the foundation for building almost any non-metallic material imaginable. Once we've defined the basic properties, we can add incredible realism by focusing on the finer details of a surface. This is where advanced mapping and shading techniques come into play. Two of the most important are bump and normal maps. These are special textures that don't add color, but instead add the illusion of depth and detail. They trick the rendering engine's lighting calculations into thinking the surface has small bumps, grooves, pores, or scratches without you having to model any of that complex geometry. This is a massively important optimization used everywhere from video games to visual effects to make objects look highly detailed while keeping them computationally lightweight. Another incredibly powerful technique is subsurface scattering, often abbreviated as SSS. This simulates the effect of light penetrating the surface of a translucent object, bouncing around inside and then exiting at a different point. It's a subtle but vital effect for a huge range of materials. It's what gives human skin its soft, fleshy appearance, what makes a candle look like it's made of wax, and what gives grapes and milk their characteristic look. Without SSS, a digital human would look like a hard plastic mannequin. These advanced techniques are what truly elevate a render from good to photorealistic, capturing the subtle nuances that our eyes are so adept at perceiving in the real world.
In the past, creating realistic materials often involved a lot of guesswork and tweaking abstract settings. However, the industry has now largely standardized on a workflow known as physically based rendering, or PBR. The core idea behind PBR is to create materials based on how they behave in the real world, adhering to principles of physics. This approach is not only more accurate but also more intuitive for artists. Instead of vague sliders like shininess, PBR uses a set of easy-to-understand parameters. The first is albedo, which represents the pure color of a surface devoid of any lighting or shadow information. Next is roughness. This single powerful parameter controls how light scatters across a surface. A low roughness value creates a smooth mirror-like reflection, while a high roughness value creates a diffused matte surface. You can define everything from polished chrome to rough concrete with this one slider. Finally, there's the metalness parameter. This essentially tells the rendering engine whether the material is a metal or a non-metal, also known as a dielectric. This is a critical distinction as metals and non-metals reflect light in fundamentally different ways. By using these PBR parameters, artists can create materials that look correct and consistent in any lighting environment, which has been a revolution for gaming, film, and design visualization. We've talked about material properties, but how do we apply complex visual patterns like wood grain, fabric weaves, or dirt and grime? This is accomplished using textures. Broadly, textures fall into two categories. First, we have bitmap textures. These are the ones you're most familiar with, image files like JPEGs and PNGs. You can take a photograph of a brick wall and apply it directly to a 3D model of a wall. This method is fantastic for highly specific or unique details like a logo on a t-shirt or the cover of a book. The second category is procedural textures. These are not based on images, instead, they are generated using mathematical algorithms. This makes them incredibly powerful. They can be generated at any resolution without losing quality, they can be tiled infinitely without any visible seams, and their parameters can be easily tweaked to create endless variations. They are perfect for patterns like wood, marble, noise, and other organic surfaces. But how do we tell the computer how to wrap these flat 2D textures onto a complex 3D shape? The most common method is UV mapping. This is the process of metaphorically cutting and unwrapping a 3D model so it lays flat, like a sewing pattern or a cardboard box unfolded. The 2D texture is then applied to this flat UV map, which the computer then knows how to wrap back onto the original 3D object. The importance of materials and textures extends far beyond creating beautiful renders for presentations. They are a critical component of the entire project life cycle, especially in technical fields like architecture and engineering, where clear communication is paramount. When we move from a 3D model to 2D construction documents, we need a way to represent different materials clearly. This is where standardized conventions like hatch patterns come in. In a cross-section drawing, a diagonal line pattern might represent concrete, while a cross-hatch might represent brick, and a wavy line might represent insulation. This visual shorthand allows builders and contractors to immediately understand the architect's intent. Similarly, color coding can be used in floor plans to designate different types of flooring or wall finishes. In modern workflows, this is taken a step further with Building Information Modeling or BIM. In a BIM model, the material applied to an object is more than just a visual layer, it's a container for data. that brick material can contain information about the manufacturer, the cost per square foot, its fire rating, and its thermal properties. This ensures absolute consistency from the earliest design visualization to the final bill of materials and construction documents, creating a seamless and error-free workflow. The landscape of digital materials is evolving at a breathtaking speed, pushed forward by remarkable new technologies. The rise of artificial intelligence is a huge catalyst. We now have AI-powered tools that can generate incredibly complex and realistic textures from a simple text description or by analyzing a photograph, slashing the time it takes to create bespoke materials. Another major shift is the power of real-time rendering. Technologies born from the video game industry now allow architects and product designers to walk through their creations with photorealistic quality in real time, which means they can change materials, lighting, and even the time of day and see the results instantly, creating a fluid and interactive design process. This interactivity extends naturally into augmented and virtual reality. Imagine a client putting on a VR headset to experience a building's interior and swap between marble and hardwood floors with the flick of a wrist, or using your phone's camera to see how a new sofa with different fabric options would look in your own living room through AR. Finally, there's a significant and important push towards sustainability. New simulation tools are being developed that can analyze the life cycle and environmental impact of material choices directly within the design software, helping designers create not just beautiful spaces but also more responsible and sustainable ones. The future of materials is intelligent, interactive, and conscientious.